Alrighty. We're going to look at two major topics today, and I'm going to go real slow, and we're going to go into a lot of depth, a lot of calculating. You're going to need your calculator today, but nothing's really complicated. So I want to start off with the binomial formula. Now this is something we've all seen many times and in multiple classes, but we may have just been exposed to it and then we move on. But we're going to tear this apart and put it back together and see if we can come up with a simple formula that we understand. Now the idea of the binomial formula, it's basically if I have a plus b to various powers. So I'm going to start like this. And our goal is to eventually come up with an a plus b to the nth, where n is a non-negative integer. So if we expand this, we know that this is going to be 1, and this is going to be a plus b. This is going to be a squared plus 2ab plus b squared, a cubed plus 3a squared b plus 3ab squared plus b cubed. Now we can do this forever and ever and ever. We know that. The trick is, first of all, noticing, in this case, every single term is of degree 3. But the exponents are in descending order for the a and ascending order for the b. That just makes it easier to keep track of. So the question is there a pattern here? Well, if we look at the coefficients only, this is how it starts. We see this. Now this goes forever. And we referred to this last day. This infinite triangle, if you will. What is this called? You remember?
Pascal.
Pascal's triangle. Now, is it the same Pascal that we had the Pascal's formula last day? Pascal, I'll put Pascal's formula. Well, what was Pascal's formula? Well, do you remember it was the inclusion-exclusion principle. It was if I take n distinct objects and I choose r of them, where r is between 1 and n in this case, then it was the same as saying, well, I'm going to set one aside, right? So from the remaining n minus 1, I'm going to choose r minus 1. This is how many ways that one object can be in this set, and n minus 1 choose r is the number of ways the object would not be in this set. Okay? So if I take any specific element. Now, what is the next row? Let's just go ahead and do the next row. Well, if I didn't know any better, I do know this. There's an a to the 4th, an a cubed b, an a squared b squared, an ab cubed, and a b to the 4th. Do you agree? There's no doubt about that part. And they're all plus signs. Now, what are the coefficients? Well, let's see. 1, 2, 3, go out on a limb and say 4. But in reverse order, it ought to be the same thing because of symmetry. And what about the guy in the middle? Well, I don't really want to multiply it out, but what is the one in the middle? Anybody know? 6. 6. Now, is there an easy way to see that? Yeah. If I look at the 2 above it, okay, you notice that the 2 above it always add up to that one, which, by the way, is an exact representation of this formula, isn't it? So if I think of this as being, well, hold on a second. Oh, eraser. I want you to think of it this way. I have 4 objects. Or excuse me, I'm sorry. I'm going to choose slots, okay? This could be, the A and the B could represent heads and tails, if you want to think of it that way. All right? So, how many ways can I distribute the things? For example, if I said, okay, I have 4 slots, in how many ways can I put all A's and no B's? How many ways can I put all A's and no B's? Well, 1. Put all A's and put no B's. How many ways can I put 3 A's and 1 B? Well, the B could go here, 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 or here. So do you agree that would be 4 ways? How many ways could I go 2 A's and 2 B's? 1, 2, 3, 4, 5, 6. How many ways can I do 1A and 3B? Well, there's 4 places I could put the A, and how many ways could I go no A's at all and 4B's? One way. And he's really excited about the binomial theorem right now. So if I look at it from that point of view, let me move this guy over a little bit. Does everyone see then that this first term, this is exactly 4 choose 0. This is 4 choose 1. This is 4 choose 2. This is 4 choose 3. This is 4 choose 4, isn't it? Based on what I was just explaining. If I said, how many ways could I put the A's and the B's? There's exactly that many ways. Okay, with me so far? So in the binomial theorem, 4 choose 0 is 1. 4 choose 1 is 4. 4 choose 2 is 6, and so on. But the previous row, what was this? This was 3 choose 0. This was 3 choose 1. This was 3 choose 2. 3 choose 1 plus 3 choose 2 added up to 4 choose 2. That's exactly what this says. Which is why, even as kids, you remember you could always come up with the next line. Every human being alive can tell me what the next line is without doing a whole lot of work. Do we agree? Because you just add the ones before it. Yes, you see patterns. But what if I was way down the list? Trying to figure out the pattern for the ones in the middle would be really complicated. But if I simply use the previous row, that becomes easy. So you're actually using Pascal's formula to complete the next row of Pascal's triangle if you don't want to sit here and multiply them out. So here's the dilemma. Okay, what if I said I have a plus b to the 100th power? And would you agree there is going to be an a to the 8th b to the 92 term? Does everyone agree that's going to be a term in there? I know because that's a 100th degree term. And I need to know the coefficient of that term. Well, I have 2 ways I can do this. I can multiply that out. Might take a few minutes, right? Or I could go to the row on Pascal's triangle. The problem is I can't tell you what this row is unless I have the 99th row. Do you agree? Which means I have to have the 98th and 97th. That could take me a while. But if this is all I want, it's impractical to have to continue on this because it is a recursion. It's impractical to have to go all the way down to the 99th row. Now I can do the 100th row. I'd rather just be able to calculate that thing. But if we see that the position, this is the a plus b to the 4th row, it's equivalent to saying I have 4 slots, how many ways can I distribute them? So what would this be telling me? I have 100 slots, and I need to distribute 8 A's in those 100 slots. How can I do that? 100 choose 8. So the coefficient of this would simply be 100 choose 8. Just like it is there. So the formula that we derive, and by the way, the author does a beautiful proof by induction. It is a beautiful proof. I'm not going to do the proof. I'm going to leave it to you guys because it's actually really, really long. The induction part, the last step is really long. It's 2 pages long. I was looking in the text. It's beautiful. Every step of the way you can understand it, but it really messes with the factorials and the combinations. It's a little heady. But the idea, if I had a plus b to the nth power, where n is a non-negative integer, we know now there's going to be, let's call it a to the k and a b to the n minus k. We know that, right? As long as those exponents add up to that. So over here, if you think of it this way, this would be a to the 4th and b to the 0. This would be a to the 3rd, b to the 1st, and so on. Okay? By the way, it doesn't matter which way you go. It doesn't matter if I put the n minus k and the k here. Why? Because of symmetry. It goes both ways. So the question is, I know that's going to be a term. What's going to be the coefficient? It's going to be n choose k. Okay? Now, by the way, it does not matter if I swap these, because that just means I'm rearranging the sum. I did it kind of in reverse because I have the higher one on the A, but it actually doesn't matter. Most people do it in this order right here. But the idea being, that's my coefficient. Well, that's a really simple thing. So the idea is, if I had n slots, and I said I'm going to distribute k A's and n minus k B's, how many ways could I do it? it'd be exactly this. By the way, is this the same as n choose n minus k? Is that the same thing? Yeah, because we know the denominator, right? The denominator of this is n minus k factorial, k factorial. The denominator of this is k factorial, n minus k factorial. These are the same thing. And that's why you have the symmetry as you move back and forth. So this is the binomial formula. We've all seen this in other classes. And hopefully everybody's seen it develop this way based on factorials. So one of the things right off the bat I want you to notice is if I take 4 to the 0 and I add it to 4 to the 1 and I add it to 4 to the 2 and I add it to 4 to the 3 and I add it to 4 to the 4, what happens when I add up that row? And add up those numbers. What do I get?
16.
I get 16. Oh, that's interesting. I added up the numbers to the a plus b to the 4th row, and I got 16. What does this row add to?
8.
4, 2, 1, 2 to the 0, 2 to the 1, 2 to the 6. Do you think there's a pattern there? What do you think? Yeah, the answer is yeah, there's a pattern there. What is the pattern though? This is a really cool one. And we use this one for a major theorem we're going to do in a little bit. If I said add up any row, well, what would the row for a plus b to the nth look like? What would that one look like? The row, well, it would be a 1. Pretty sure we all got the first row. And then the next one's always what? N. And then the next one is, if you will, just n choose 2. And the next one's n choose 3, and on and on and on until I have n choose n minus 1, and finally n choose n. Well, technically, what is 1?
N choose 0.
It's n choose 0, and what is n?
N choose 1.
It's n choose 1. So if I have consistency now, what if I said, I want you to add up these guys? What does it seem like they're going to add up to based on the first few?
2 to the n.
It sure feels like that. Does everyone agree? If I asked you what the next row was, you could all tell me by just looking at this row, right? 1, 5, 10, 10, 5, 1, and those numbers do add up to 32. Wow. I'd like to be able to prove this. Whoa. How could I prove this? Well, if I asked you to do a plus b and then raise that to the nth power, then I need to put the terms in here. So there's going to be an a to the n, here's going to be an a to the n minus 1b, here's going to be an, and so on, right? A to the n minus 2, b to the second, all the way down to here, and this is going to be a b to the n. Do we all agree? That's what's going to be here if I actually said expand this. Here I was just writing the coefficients. Now I actually, if I put in the terms. How can I prove, so I'll write it out the long way. I'll just write the first few terms. How do I prove that this is and all the way to the n, and choose n, a to the 0, b to the n. Okay, we know this is true. This is what the derivation is. If I said I want you to add up the coefficients, how can I prove that that adds up to 2 to the n? That's the easiest part of all. Let a equal b equal 1. Then what will you have on the left side?
2 to the n.
2 to the n. What will you have on the right side? N choose 0 times 1 plus n choose 1 times 1 all the way to n choose n. Isn't that beautiful? That's the proof. That's it. We just proved this. That's kind of cool, isn't it? So if I add up these combinations from 0 all the way to n, it will always add up to 2 to the n. And the proof is simply, because we know this is the binomial expansion, if I replace a and b both with the number 1, then I prove 2 to the n equals that sum. So one way this is often written, and this is actually a very powerful formula, by the way. All right, I'll use k. From k equals 0 to n, and choose k. This is actually a very powerful identity. Okay? You with me so far? Now the binomial expansion is a little more complicated. The binomial expansion looks like this, all right? So using this, I would like to expand. Let me grab a problem out of the text. So there's some great problems in the text. What if I had something that looked like, I'd like you to be able to tell me what this is without actually doing a calculation. By the way, I can do a calculation. So if I expand this, okay, if I expand this, what am I going to get? Well, when k is 0, I have n choose 0, which is 1, times 4 to the 0th power, which is 1, okay? So I would get 1 plus. Agreed? Now, what if k is 1? Then I have n choose 1 times 4. Then I had an n choose 2 times 4 squared, all the way up to n choose n times 4 to the n. Great. But if I don't tell you what n is, how in the world would you add that up? Oosh. Well, what if I did tell you what n was? Then you could add it up, couldn't you? But it'd still be busy. What if n was large? Do you really want to add that up? No, we want to be clever. How do we be clever? See this here? I want you to make this look like this. Any ideas? Anybody got an idea? To make those look exactly the same?
1 to the n minus k.
Now stare at that for a moment. Have I changed the value in any way? Have I changed the value? No. But there's my a to the k. There's my b to the n minus k, which means that this has to add up to what?
A plus b to the n.
A plus b to the n, so this has to add up to 4 plus 1. Oh my goosh. You gotta admit, that is cool. This sum, and by the way, assume n is large. Assume n is large because you do not want to do this and expand this by hand. You never want to do that. When we started this process, we did really small experiments. I said, flip a coin 3 times. Let's write down all the outcomes. But on one of your quizzes, I said, flip a coin 4 times. And all of a sudden, you go, man, that was kind of messy, wasn't it? I got to write down 16 outcomes. What if I said flip it 6 times? You really want to write down 64 outcomes? Do you think you would get all of them down, or we might miss 1 or 2? All of a sudden, it was too big to be practical. Then we started talking about, lineups of a baseball team being in the, bazillions, right? Hundreds and hundreds of billions. Is like, no, I'm not going to list things. If I have to list things or actually do the physical calculations along the way, it can be overwhelming. If n was a large number, even if I knew the value of n, well, let's just say, keep it simple, n is 10. That is a lot of calculating, and I'm adding up a lot of numbers, yet we've just proved this. Now, there's a whole bunch of problems in the textbook that are of this nature. Sometimes they throw in variables and things like that, and there's some clever. So let's do another one, but let's do one that requires a little bit more cleverness this time. Some of these are just really, really cool problems because they will help us do counting of big things in a lot of ways. All right, so let's suppose, here's a simple one. Now this one should be really easy, actually. Why should this be easy? Easier than the last one. We had to create this, and so you could figure out an A and a B. Do I have to create anything, or is it already there? It's already there. It's just there's a variable and a number. So what do you think this is going to be?
X plus 2, 2.
Yeah, x plus 2 or 2 plus x, it doesn't matter. I'll write it as 2 plus x because that's the order, but it doesn't make any difference.
Minus 1.
I'm sorry?
Whole thing minus 1 because we start from k equals.
Oh, I'm sorry. Let me start there. Thank you. Yeah, you'd absolutely correct. We'd have to subtract 1 from that. I don't want to subtract 1. I just wrote it badly. Now see, that was easy, wasn't it? Now, could we ever get a minus sign in here? How would we get a minus sign? Well, what if I wrote it like this? Let me grab this one. This one looks sufficiently evil. I'm using K. In the textbook, the author just keeps changing. It doesn't really matter. Correctly. Yeah. Okay. Now, this is tough. Sorry, I can't read my own writing. This is n minus k. My bad. I can't read my own writing. 4 to the n minus k, 2 to the k. And the idea is, can I answer the question as is? Does this look like the binomial formula? The answer is no. Why? Because of that. If that wasn't there, this would be easy. Agreed? What would it be? It'd simply be 4 plus 2 raised to the nth power. Well, that's a piece of cake, but it's not. What do I do with that? Well, can I glue that to one of the terms? Which one?
2.
Because they have the same exponent. So if I took -1, that's using just the property, whoops. If I said a to the n, b to the n, we know that's a, b to the n. That's an exponent property. So if I have thing to the k times other thing to the k, it would be the same as just saying what? I have 4 to the n minus k times -2 to the k. Do we all agree with that? So therefore, this would be what? 4 plus -2 raised to the n, or simply 2 to the n. Whoa. Now, I really wouldn't want to expand this. Right, that would start to get complicated because you're adding and subtracting, right? Every other term would be plus, minus. But by just simply using the binomial formula, okay? Yeah, there's a little bit of cleverness, sure. But this is pretty straightforward. I like this. So one of the main things we use the binomial formula for is either expanding or calculating coefficients. So let's do both. Okay, what if we have something like this? I'll keep it really simple. I've got 2x plus 3y to the 4th power. I want to keep this really simple. I want to expand this, okay? But to expand this means I want to write a polynomial without any parentheses, but I really don't want to multiply it out by hand. Now, a lot of folks do that. They when you're cubing something, people will multiply it out the long way, not realizing if you know the coefficients, the 1, 3, 3, 1, you save yourself a lot of time. Do I know the coefficients? Yeah, we just said it was 1, 4, 6, 4, 1. If it was a plus b, but this isn't a plus b, it's other stuff. Okay, so what was a plus b to the 4th? That was a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. How do I use that to my advantage? Well, in this case, this is my a, this is my b. So it's really not that complicated. So this is going to be 2x to the fourth power plus, and I'm going to write it formally. 4 choose 1, that's where the 4 came from. 2x to the third power times b, which would be 3y, plus 4 choose 2 times 2x to the second power times 3y, also to the second power. There's my a squared b squared. 4 choose 3, 2x to the first power, 3y to the third power, and then finally just 3y to the fourth power because we know the last one has a coefficient of 1. So if I use the binomial expansion, I've got this. I didn't sit there and multiply binomials together and gather like terms. That takes way too long. Plus, filled with errors, agreed? We're going to make mistakes. But if I do this, what's my answer? Calculator or in your head, doesn't matter.
16.
So now 16x to the fourth. By the way, if I don't do anything else right, I do know this. I know my answer is going to look like this. Agreed? Because x and y were both originally to the first power. So I have a 3 times a 2 cubed times a 4. What's that?
96.
So 96. Let's see where am I? Now here I have a 3 squared times a 2 squared times a 6.
216.
216. Here I have a 3 cubed times a 2 times a 4.
216.
Also 216. And then lastly, a 3 cubed. And there's my expansion. Did I labor? Not at all. No, this was actually fairly simple because I knew the form the answer was going to take on. Okay, that's one version of the question. Now let me give you a different version. All right, I have 2x squared minus 4y to the 10th power, and I want to find the coefficient of x to the 12th, y to the 14th. Now, before you do that, if I just randomly made up exponents, is there necessarily going to be a term? Look at the last example. You knew these before you started, agreed? If I had said, find the coefficient of y to the 6th power, you'd say there isn't a y to the 6th power term. Right? You knew what all the exponents were. Is there actually going to be an x to the 12th, y to the 14th?
No. No.
Why not?
There's no y to the 14.
Sorry?
There's no y to the 14.
But because of that. This is my whole point is you'd say there isn't a term that looks like that. So now I'm going to change the problem. What if I make that a 20?
Yes.
Now, how did you come to that conclusion? The easiest way.
14 plus 6.
Yeah, if you looked at the y to the first power, if there's a y to the 14th, then the other term has to be to the, what? 6th, because those have to add up to 20. Oh, okay. So I want to remind you, this is not a trick question, this is a tricky question. I've seen this come up many, many times mathematically, especially in a probability type of problem. I want to find that coefficient, and you go, wait a minute, there isn't a term that looks like that. I'm wasting my time. Because if I just randomly said, this is very similar to, I said, I want you to flip a coin 3 times. What's the probability of getting 4 tails? You guys told me the probability is 0 because that isn't a possible outcome. You remember we did that on day one? That's the same thing. So if I said, I want to get this, you'd say that's not a possible outcome. I also need to know when something can't be done. It is actually very important. So now do we agree this can be done? Do I need to expand this thing? I don't want to do this. There's going to be 21 terms, right? 0 through 20. I only need the coefficient of one of them. Can we write it down? Let me tell you, how do I write down? Well, first of all, it's going to be 20. Oops. Oh, yeah, it's going to be 20 choose what?
6.
20 choose 6 or 20 choose 14. It does not matter because they're the same value. Agreed? Then times what?
2 to the 6.
We're going to have this one to the 6th and this one to the 14th. Now, what a lot of folks, they'll go like this. I'm going to do this. What do I do with that? Do I ignore it?
Inside the parentheses.
Inside the parentheses, good. This is the actual term I'm looking for. Do we all agree? This is huge. Boy, my God, when would you have ever done something like this? This is actually an intermediate algebra, by the way. If you go way back, algebra 2 in high school, you actually, well, you were supposed to do stuff like this. Late in the course, this was huge because that's when you first were exposed to the stuff. Did it mean you understood it? Oh, heck no. But could you calculate it? Sure. The reason I'm writing it out, because I want to ensure I get the right exponents. Because if I didn't write the x squared and the y to the first power, I could have set it up incorrectly, and I wouldn't have known. But because clearly I'm going to get an x 12th, y to the 14th, does everyone see that? I'm going to get this. I'm looking for the coefficient, but I need to ensure that I have the right exponents. So, what is my numerical value? It's going to be this quantity times 2 to the 6th times -4 raised to the 14th. I have to consider the negative because what if this exponent were odd? We do realize this is going to alternate in signs, right? So I do need to do it just like that. Never just ignore it. So that number should be really large. Anybody got it yet? I need everybody to do this because you got to make sure you can do this. I had a calculator when I came to class. Oh, here it is. All right, so let's everyone do this on your own for a moment.
So 6.6589 times 10 to the 14th power.
Does anybody get something different?
No, the same thing.
So what did you get?
666 trillion.
666 trillion. Okay. Does anybody get it without scientific notation? Does anybody have a graphing calculator that you have? I'm just curious. Does anybody? Oh, okay. It'd be nice if it's on the order of 10 to the 14th power. Yikes. Well, 10 to the 12th is a trillion, so this is on the order of over 600 trillion. I want to discourage you from multiplying this out. Just saying. Could you imagine trying to keep track of coefficients? You'd be amazed. I've taught these classes where people do these, and no, I'm just going to multiply it out. No, you're not. No, that would be silly. But that's the answer. And that was actually pretty simple to come up with. Okay, because I just needed a calculator, but I had to know where to put the numbers in. So the binomial expansion is really, really important. So, if nothing else, I know that if I have a sum and I raise it to an integer power, a positive integer power, I know now how to calculate the coefficients. We start with this. This is the key. If I know how to expand this and I know all the coefficients I now know are combinations. Right? N choose k, where k is ranging from 0 to n. Now, if a and b themselves have coefficients, that's a non-issue because I'm basically then just raising that term to the appropriate power. That's the key. If I understand this, then this segue is actually pretty simple. Most of the time, you're not asked to expand things because there's too many terms. You're asked to find a specific coefficient. But the idea is I could expand it if I wanted to. Everybody okay with that? Okay. Now, I'm going to do a problem that we do in statistics all the time. I'm going to define something, and this, by the way, from a statistical standpoint, this is one of the more important things. In graduate school, this is one of the more important things we studied, and it's the concept of expected value. Now, anybody who's had statistics, you remember that, hopefully, and you spend a lot of time on that. Expected value is not what is going to happen, it's the highest probability outcome. So you could think about it this way. Excuse me. You work, you have a job, okay? And the one I like to use in stats classes, let's say you're a contractor in Seattle. Why Seattle? I come from a family of contractors. What is the contractor's worst enemy? Rain. Most of the time you can't work in the rain, right? You can't put on a new roof in the rain, you can't do certain things in the rain. And you're a contractor in Seattle. So rain is a constant issue. So it's something like this. If we work today, here is how much money we're going to make. If we don't work today, here's how much money we're going to lose because we still have to pay for things, you know. The probability of rain is such, so therefore the probability of no rain is such, meaning I can calculate the probability that I'm going to work today. What if the probability of working today, keep it simple, was 0.5? And the probability of not working was 0.5. Then what can I expect today's outcome is going to be? Well, basically, let's just say, we'll keep it really simple. You're an employee. You're going to make $100 if you work today, but it's going to cost you $20 if you don't work because of maybe you already had to go park and whatever. If it's a 0.5 chance of rain, then you'd say, that's $50 I'm going to make, $10 I'm going to lose, the outcome is $40. But wait a minute, I'm either going to make $100 or I'm going to lose 20. 40 isn't a possible outcome, but it would be the expected value. An easier way of thinking about this, what if this went on day after day after day after day after day, then over the long term, what was your average outcome? Then it'd be really easy to see, oh, okay, if in 100 days I actually worked 50 of them, and I didn't work 50, here's exactly how much money I came away with, and that's exactly $40 a day. Does that make sense from that standpoint? I'm going to flip a coin 10 times. We know how to calculate all of the outcomes. I could have 10 tails, I could have 0 tails, I could have 5 tails. But if I flip it 10 times and it's a fair coin, what is a reasonable expectation? 5 of each. Does that mean that's what I'm going to get? No, it's the highest probability. We're going to actually show from a calculation standpoint that's exactly what you can expect. I'm taking a multiple guess test. We're going to do this one also. There's 100 questions. I walked into the wrong class. There's 5 responses to each question. I walked into the wrong class. I didn't realize. So I guessed on every question. What is a reasonable expectation? If there were 5 responses to each question and there was 100 questions, doesn't it seem reasonable? I ought to get a 5th of them right. Does that seem reasonable? Yeah, I should get about a 5th of them right. And we're going to be able to show from a calculation standpoint what the expected value is sometimes a common sense thing, and sometimes it's more complicated than that. So we have to set ourselves up. So first of all, we have what is called the random variable. I'm going to use statistical terms because that's where this comes from. A random variable is basically something that represents every possible outcome to that experiment, but as a count. It's a numerical value. So for example, if it were a coin flip, I have to be counting something. I have to either be counting heads or tails. If it were I'm rolling the dice, I have to be counting very particular outcomes. Maybe I was calculating the outcomes where I get a 7. Or maybe I'm just talking about the sum. Okay? The expected value, or the random variable, in stats, we usually use a capital X. I can have more than one. We're not going to do more than one in this class. That's actually higher level statistics. Okay? So if I said, here are the possible outcomes, the X could equal X1, X2, all the way up to Xn. Whatever those are. Now, if it could be, these could be the sums of a dice roll, in which case those numbers would be 2 through 12. This could be I flip the coin 10 times and I'm counting tails. Now it would be 0 through 10. This could be you had children, how many girls did you have? Well, n would be the number of children you have, so the number of girls you have would be 0 up to n. Right? The random variable usually, in most cases, is a count. We're going to look at other situations. It could be, in the last example, the random variable was $100 or it was negative $20. Because those were the only two outcomes in my example a moment ago. You with me so far? Now, every one of these has a probability. So let's say the probability that x equals any individual outcome, this is big X equal, and these are little x's usually. We're going to call that little p with a subscript divide. This is big P. Big P is the probability of, big X is the random variable. Little x is the particular outcome, little p is the probability of that little outcome. Just to make it easy on ourselves. All of these outcomes are mutually exclusive because I am counting. You can't have an outcome of exactly 3 tails and an outcome of exactly 4 tails and somehow they overlap. Agreed? If I said, how many children do you have? you're giving me discrete counts. There can't be any overlap. Okay? So tell me about the sum from I equal 1 to n of p, little pi. Tell me about that. I'm adding up the probability of this outcome, this outcome, this outcome, all the way to here.
Watch.
It's got to be 1. It's got to be 1. All of these are mutually exclusive. That definitely makes things easier when there's no overlap. We previously looked at things that had intersections. And tomorrow's lecture, we're going to be looking at things mainly that have intersections. But here we're simply counting outcomes. So there should not be intersections. Okay? So now we define expected value, which we usually use a capital E, expected value of x, because there's also a variance of this. We're not interested in that. In statistics, we calculate variance also. The expected value of the random variable is simply the sum from I equal 1 to n of little xi times little pi. It's actually that simple. Take each outcome, multiply it by its probability, and then add them all up. So in the case a moment ago with the contractor, you made $100 with a probability of 0.5. You lost $20 with a probability of 0.5. If I then multiply and add those outcomes up, that gives me the expected value each time. Another way of thinking of expected value, again, think of it like a long-term average. Okay? So we're going to talk about this in a bit, because that's also a really important thing. So if this is the case, I want to start with something relatively simple. We're going to flip a coin. I'm going to keep it really simple. 3 times. We are counting tails. We have to count something. We're going to count tails. So x, oops, sorry. Let x be the number of tails. Then what are the possible outcomes that x could be? Heads. Well, no, numbers of tails. Just keep it simple. We're going to list the outcomes in a moment, but I'm going to flip a coin 3 times. What is the possible number of heads I could get? None. 1, 2, 3. Do you all agree with that? Now, I'm gonna write down the individual outcomes because it'll make it easier. But what if I said we're going to flip the coin 20 times? Do you really want to write the HHHTTT? No. You want to know how to count them quickly. So I'm only doing 3 because listing the sample space here makes it much, much simpler. Okay? So if I list my sample space, my random variable is what I'm counting. I could have counted something else. But my sample space is going to be H, 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 T, H, T, H, H, T, T. T, H, H, T, H, T, 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 H, T, T, T. That's my sample space. So now, what is the probability that x equals 0? Now, in this context, I'm saying, what is the probability that my random variable takes on the value of 0? Most people would just write, what is the probability of 0 without any loss of generality. This is the formal math notation. I'm saying the same thing, it just takes less time to say this. Do you agree? So, can you tell me if these are capital P's. The probability that my random variable took on the value of 0, meaning I have 0 tails. How many of these outcomes had 0 tails? So what is this? The probability would be 1 out of 8. Now, how many of these outcomes have exactly 1 tail? 3 of them. So 3/8. How about 2 tails? Also 3/8. And 3 tails. 1/8. 1, 3, 3, 1. Does that surprise us at all? No. I kind of seen that one coming. Now, I haven't even defined anything related to what we're doing. I just said we're going to do a coin flip 3 times. We're going back to the first date. Okay, I haven't given you any formulas or nothing. Can you now tell me on 3 coin flips what is the expected outcome? Yeah. Let's do exactly this. It's 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. That is exactly the expected value because it's a fair coin. Remember, if it was not fair coin, all things are different. And what does this come out to be?
1.5.
Huh. That's interesting. If I flipped a fair coin 3 times, I should expect 1.5 tails. Is that a possible outcome, by the way? A moment ago when we said, what was the expected value of the construction worker? We said $40, but that wasn't an outcome. No, I said, think of that as a long-term average. Oh, so here's the way I want you to think about this. I want you to take a coin, flip it 3 times, write down how many tails occur. Now do it again. Do it again. Do it again. Do it 100 times. Do it 1,000 times. Are you going to see 0s, 1s, 2s, and 3s popping up? Yeah, that's all you're going to see. You're going to add all those up and divide them by 1,000. What are you going to see? A number pretty darn close to 1.5. 1.5 is going to be the long-term average every time you flip a coin 3 times. Does that make sense? Why 1.5 is the answer? Now, I haven't shown you mathematically. We just physically did it. Now I'm going to define this in a bigger sense. Okay. The most important type of distribution that we study in statistics is the normal distribution because that's the thing that occurs most likely. But from a probability standpoint, the most important distribution is what is called a binomial. A binomial distribution has a few key components that makes it binomial. If I said, here's a deck of cards, pick a card, any card, and you picked the card and you kept it. And then I said, let's do it again. Do probabilities change because you kept the card? Yeah. I have the urn filled with different colored marbles, and you pulled out a marble and you set it down. And does the probability change when you're doing that problem? Yeah, that's not a binomial. A binomial would be something like flip a coin, guess on the multiple guess. So why? Because here's what makes a binomial distribution. Well, first of all, what do you think we can interpret from the bi?
It's got a yes or a no, like a true
Yeah,
false.
this is where the term binary comes from. There's only 2 outcomes. Whether it's true, false, 1, 0, yes, no, however you want to say it, there's only 2 possible outcomes. In the world of statistics, we call it success and failure. In this problem right here, what was a success? Flipping a tail, because that's what I was counting. What was a fail? Flipping a head, because it was the other thing. There were only 2 outcomes, heads and tails. If I'm rolling a die, there are 6 outcomes. That's not binomial, unless, how could I make rolling a die binomial?
Odd or even.
Okay, or keep it simple. You rolled a 6, or you didn't.
Or you didn't.
Oh, okay. Would you agree that every outcome on a die is a 6 or it's not a 6? Now it's binomial. So the first thing is, for binomial, there can only be 2 outcomes. And we generally call them success and failure. Not because you succeeded or you failed. We call a success the occurrence of the thing you're actually counting. And if it didn't happen, then we call that a fail. Okay? There must be n trials. And what I mean by this is huge. That means you have to know how many times you're going to do it before it starts. I'm going to give you a really simple one. I want you to flip a coin until you get 10 heads. How many times are you going to flip it?
At least
At least 10 times. But can you tell me how many times you're going to flip it? No. Could you have gotten it in 10? Yeah. But it's probably going to take you at least 20. Probably, right? But you got it in 18, you got it in 23, you got it in 17, you got it in 16, you got it in 13, you got it in 9. Wait a minute. That's not possible. But do you agree that you couldn't tell me what the n is if I said do it until something happens? That's a completely different type of problem. So n trials, I have to know before. I flip the coin 10 times. Okay, great. There are n trials. The probability of success, which we call little p, and failure, which we usually call little q, which of course equals 1 minus p, remain the same throughout. If I wanted you to roll a die, what is the probability you rolled a 6? 1/6. What's the probability you did not roll a 6? 5/6. Now I want you to do it again. Do those probabilities change? You're going to flip a fair coin. The probability of a head and a tail are both 1/2. Now I want you to do it again. Do those probabilities change? No. No. So the key is the probability of success and failure do not change throughout the problem. I want you to pick a card, any card, now set it down. Whatever I'm calculating, is the probability going to change on the next trial? Yes. Oh, okay. So that's not binomial. So in a binomial, two major things. Well, besides the fact there can only be 2 outcomes. By the way, if I was counting all the faces on a die, there's another name. It's not binomial. It's called multinomial. And it has its own set of rules. We're not doing that one. We're doing binomial. So there's only 2 outcomes. You're doing it n times. The probability of success and failure never change. And by the way, because the probability of failure is 1 minus p, that means p plus q has to add up to 1. Okay? So this is it. So a coin flip is probably the simplest example that most people think of in a binomial. But the coin flip is a little artificial because the coin flip is the situation where p and q are both 0.5. Binomial experiments, they could be anything. So deciding that I'm going to start with a coin flip, it's the easiest one, but again, it's artificial because it's the only one where the p and q are the same. So like the rolling the 6 or guessing on a multiple guess test, that's probably a better example. So here's the thing. If x represents my random variable, I did n trials. In my n trials, I can have 0 successes, I can have 1 success, I can have 2, I can have 3, all the way up to n. And again, if the probability that x equals little xi, we're going to call little pi, then the expected value of x, we just said a moment ago, right? We said this a moment ago. So it's xi times pi from I equal, in this case, we'll say I equal 1 to n. Hold on. Well, actually, I'm not going to call it xi. Sorry. Let me do it this way. K equal 1 to n of k times pi. But what's pi? Think about this. I'm going to flip a coin 10 times. What's the probability that I got 3 tails? I don't want to list the HHHTs. Let me keep this really simple. I'm going to flip a coin a whole bunch of times. What's the probability you get exactly, or in other words, how many ways can I get exactly 3 tails? That's an easier way of saying it. How many ways can I get 3 tails? I'm going to back up one step. I'm going to go back to the probability part. I'm going to go back to this. Well, I got to pick which places I'm going to put them. So if there were n trials and x successes, how many places can I put the x's? It'd be n choose x, wouldn't it? So what is this probability? It would have to be n choose x. That's how many ways it could be done. Times the probability that I was actually successful, which means I was successful x times. How many times was I, I'll put the Q. How many times was I unsuccessful? If there's n trials and I'm successful x times, how many times am I unsuccessful? N minus x. This is the probability of any particular outcome in a binomial experiment. Now, why is the coin flip so nice? Because P and Q are both a half. That makes this calculation really, really, really simple. But in general, it's not. So this is the probability in a binomial experiment. This looks real familiar, doesn't it? Doesn't that look like the whole a plus b raised to the nth power thing? That's the probability of the outcome. So when I want to do the expected value, and I'll just put little x now. Whoops. I'm sorry. The expected value of little x is, I'm now going to multiply this out. X, n choose x, p to the x, q to the n minus x. And I'm going to add all these up, starting with 0, because 0 successes is a possible outcome. This is complicated. This is very complicated. And I'm going to show you how it works out. Common sense. I'm going to flip a coin 2 bazillion times. What's the expected number of tails? I flipped it 2 bazillion times. How many tails should I expect? 1 bazillion. Is that what I'm going to get? No. No, in fact, if you've got a stats class, and maybe you did this and maybe you use computer software to help you, I'm going to flip a coin 100 times. The probability of exactly 50 tails is really small, but it's still the highest. 49 and 51 are slightly smaller and the same. 48 and 52 are slightly smaller, but the same as each other, and so on. And then when I do this, and if I could add them all up, the calculation would still come out to be the expected value is the 50, the common sense answer. Some people refer to this as the law of large numbers. Everybody's heard that statement. Most people have no idea what it means. It refers to a binomial experiment, first of all. If something has a set probability, and I do the same thing over and over and over again, what I actually see, the empirical, should pretty much mirror what I expected to see, the a priori. You guys heard that term? That's the prior knowledge. If I said, I'm going to flip a coin, the probability of a tail is 0.5, but I haven't even flipped it yet. Yeah, that's the theoretical probability. What I actually physically observe is called the empirical. And those two should be pretty darn close when I actually do it, if my probabilities are correct. So I want you to do the same thing over and over again where the probability is set. It's not changing. Then what I actually observe should pretty much mirror what in theory I was supposed to get. Will it be exactly the same? No. Why? Because that coin doesn't have a chip in it with memory to keep track of how, oh, shoot, I landed heads last time, let me lean this way this time. No, the experiment starts over every time. Right? That's why in games of chance in general, okay, in games of chance in general, you're going to play at a casino or something, the expected value has to be negative for you. Why does the expected value have to be negative for you? Why can't it be positive?
Because the casino would have to shut down.
Yeah, they go bankrupt today. Yeah. The casino has to make some money. They have to make some money, pay their employees, keep the lights on, keep giving you those free drinks to encourage you to keep gambling. No, your expected value has to be negative or there can't be a casino. Now, you don't want your expected value to be hugely negative. We're going to do some of those calculations also. So this is gnarly. Would you agree this is gnarly? So here's what I want to do. I want to calculate this for a binomial experiment. This is, to me, this is beautiful mathematics. Nobody's ever seen this in a stats class because this is way beyond a stats class. I want to actually calculate this. Now, we messed around with the binomial stuff before. And if I didn't have this darn x in the way, this would have been easy, wouldn't it? If the x wasn't there, I already know what the other part's going to add up to. Because p and q have to add up to 1. Oh, so wouldn't this part just be 1 to the nth power? In other words, take the x out for a moment. Doesn't this have to add up to 1? It's literally an expansion of a plus b. In this case, this is p plus q, this part here. Take out the x for a moment. That is exactly what this would have looked like, right? And yeah, and choose, I was using a k before, I'm using an x right now, it doesn't matter. But that's exactly what this would look like. But that throws a monkey wrench into it. So here's what we're going to do. Okay. X represents the number of successes. So this means if I start with 0 successes, there's only one way to do it, and that's to have all fails. And choose 0. What's the probability that I fail every time? The probability of failure raised to the nth power. We did this before. Remember when we calculated the probabilities of at least 1? We calculated what's the probability that I fail every time? Now, what's the probability that I'm successful exactly once? That'd be n choose 1, and p, probability of success, raised to the first power. Now I failed n minus 1 times. I multiply that probability. Okay, that's just the sheer probability part. I multiply by the number of successes. So off to the side, I want to do this. If I do this calculation right here, that's x times n factorial over n minus x factorial x factorial, is it not? Oh, sorry. So how about if I write like this? Does anything cancel? Stare at that for a moment. Make sure you believe it. This minus this. Does everyone see it? These are true. I figured out a way to manipulate this a little bit. So this now becomes, oh, by the way, I'm going to go one more step. This usually isn't if you actually see a proof of this, this step is usually left out, which is unfortunate because it's kind of important. I'm saying starting at 0 and starting at 1, I get the exact same result. How could that be? Because if I'm starting at 0, what's the first thing I'm multiplying by? 0, which means the first term of this is always 0. Do you remember when we did the coin flip a moment ago? I said 0 times 1/8 plus 1 times 3/8 and so on. Your first term has to always be 0 because it's the probability of 0 times 0. Okay, I'm doing that because I want to replace this with this. And then, hold on, make sure I've got everything. Yes. And then that's p to the x and q to the n minus 6. Okay. I'm going to erase this now because I've derived that. You see that. Now, next clever step. I'm going to take p to the x, and I'm going to write it as p times p to the x minus 1. Is that legal? Sure. And by the way, x is now starting at 1. That's important. This can't be a negative number. X can't start at 0 because that would be impossible, wouldn't it? So I'm going to replace this with p times p to the x minus 1. Now, what's the only thing changing x? X is the only thing changing. So if I had a 3 here, could I pull the 3 on the outside? N is a constant. Can I pull the N on the outside? Can I pull the P on the outside? Yes. You're going to like this. This is now equal to NP times. What I have left. Now that just looked goofy. I want to shift it so it starts at 0 again. If X is going from 1 to N in this statement here, right, then the highest I could have is N minus 1, N minus 1. Okay? I would like to shift that to start it at 0. So rather than do a shift, what if I do a simple replacement? I'll just do this. Let's call K X minus 1. Then what would X equal? K plus 1? Then can I write this as NP? I'm doing it that way so it's more obvious. Times the sum from K equals 0 to K equals N minus 1. Because that would mean that X is N. Everybody see what I just did? This has exactly N terms in it, doesn't it? This still has exactly N terms because I'm starting at 0 and I'm ending 1 less. Now, what's my thing here? N minus 1 is still N minus 1, but now I'm starting at K. This would now be P to the K, and this would be Q, or if you want to write it, well, I'll write it as Q. Q to the N minus 1 minus K. And those two have to add up. Now stare at that for a moment. Isn't this just the expansion of P plus Q to the N minus first power? Isn't that exactly what the binomial theorem says? Not to the N minus 1. But what's P plus Q? P is the probability of success, Q is the probability of failure, so this is just 1. So this entire sum is simply 1, which means the answer is, to me, this is one of the coolest results in all of statistics and probability. This is the formal mathematical proof that if you have a binomial experiment where the probability of success is P and you perform it N times, you can expect N times P. Well, so wait a minute. If I'm flipping a coin and the probability of success is 0.5 and I do it 1,000,000 times, then I should expect 500,000 tails? Yes, that's exactly what it means. I'm going to roll a single die and the probability of a 6 is 1/6. I'm going to do it 600 times, then I should expect 100 sixes. Yes. Because if I actually listed every outcome, calculated every probability, that would take a long time. I'd add all these up. I would always see exactly the expected value, NP. How many have had stats before? You knew the NP. Why? Because they told you it was NP. They told you it was NP. Why? Because that's the proof. By the way, I in my entire lifetime have only seen this proof one time. And it was in a graduate stats course. This is not a proof most people see because most people have no idea where it came from. We can understand this now. I'm not going to ask you to reproduce it, but isn't that cool? A binomial experiment, I'm going to do it N times, the probability of success, it's never going to change. That's why if I have that 100-question multiple guess test where there's 5 responses to every one and I just randomly guess, I should get 1/5 of them right. Why? Because my probability of guessing correctly is 1/5. Now, where do we use this in real life all the time? Well, it's hard to say investing works this way because things are constantly changing. What I love, this is called Steph Curry mathematics. Anybody know who Steph Curry is? He's a basketball player who he's robotic in that he just, especially from the free throw line, just doesn't seem to miss. So I always say, okay, game is on the line. You're betting on the other team. Let's say we're down. The Warriors are down by 1 point. I'm a Laker fan, just so you know. Warriors are down by 1 point, but I'm a big Steph Curry fan. Steph Curry gets fouled. He's going to the line for 2 shots. There's basically no time left in the game. You're a betting person on the other team. Is it looking good for you? Because he makes over 90% of his free throws. So let's make it simple. Let's say he makes exactly 90% of his free throws. Can you tell me then what is the expected number of free throws he's going to make if he shoots 2 and he makes 90% of his free throws? What can we expect? 1.8. So you can't make 1.8. But let's say the same scenario occurred 10 times. Then making 1.8 on average means he would have made 18 out of 20. Oh, that makes perfect sense. So if you're a betting person and the expected value was 1.8, you'd say it's really likely he's going to make them both. Can you calculate the probability he makes one and misses one? Yes. Can you calculate the probability he misses both? Yes. But this is how we do it in sports. So a lot of times people say, well, what's the probability before it happens? This. So I used to love using Kobe Bryant. And I'd say, because it's really easy to just look up on the internet and say, what is his career free throw percentage? In other words, what's the probability he makes a free throw? Now, he's going to go to the line 10 times. What's the probability he makes at least 5 or makes at least 7 or makes... You can do all of these using the binomial probabilities. And it's exactly the formula we are asking, but the P and the Q. The P would be his probability of making the free throw. The Q would be the probability of missing. Steph Curry's a great one because his probability of making is really close to 1, but it's not exactly 1. So is it possible that he misses both? Is it mathematically possible? Yes. It's not a very high probability. So the expected return is what the average would be over a long period of time. That's the easiest way. Because more often than not, the expected value may not even be an attainable outcome. When we flipped the coin 3 times a little while ago, our expected number of tails was 1.5. That's not a possible outcome. No, but it's a perfect average outcome. So everybody in the classroom, you're going to flip a coin 3 times. Our class average should be right about 1.5. Might it be 1.6 or 1.4? Sure, because the coins aren't talking to each other, right? There's no memory going on. But that should make sense to you from that standpoint. Okay, you with me on that? So in a binomial experiment, the expected value is really the common sense answer. That's what's really, really cool about that. Now, let's look at a different one. Okay, now we're going to talk about something called a fair game. And this is, for the gamblers, this is really the important thing. Okay. Always assume there are 2 players. It could be me versus you. It could be you versus the house, in a casino. But there's 2 players. What is the probability that you win versus the probability they win? Those have to add up to 1. And what is the expected return overall? So we're going to have a really simple game. We're gonna do coin flips. That's our game. It's coin flips. So we're gonna flip a coin. If I get tails, you pay me $1. If you get heads, if you get tails, sorry, I pay you $1. And we're gonna do this all day long. At the end of the day, what do you expect? What do you expect? If I get tails, you pay me $1. If you get tails, I pay you $1. It's a fair coin, and we're gonna play all day long.
Break even?
At the end of the day, yeah, you expect we broke even. You'd expect we both won the same number of times. Now, will it be absolutely? No, but it's going to be pretty darn close, we would expect, because it's a fair coin. So you'd say in that situation, both of our expected returns actually should be 0. Does that make sense to you? That both of your expected outcome should be 0. So we call something a fair game if the expected value in the end is actually 0. We're going to do it from a money standpoint, by the way. If the expected return is $0, meaning nobody's making money, nobody's losing money. Now, at a casino, it can't be $0 because we just said a moment ago, they couldn't stay open. Okay? They actually couldn't stay open. I always find this interesting because most people don't know this, is because it's so it's such an odd statistic, but do you know the game of chance with the highest expected value? Believe it or not, it's a roulette wheel, where you're just betting red versus black. You're going to win about 47% of the time. There's no, I've done some research. No, I'm not talking about you're a card counter at blackjack and you've played long enough to actually gain an advantage, because you're never going to, because they play with too many decks and they reshuffle too often. You're a good poker player and you're playing with strategy. No, I'm talking about you're just going to a casino and playing games of chance. You know, slot machines are really poor. But a roulette wheel, I'm gonna just keep it simple. Okay, you have, you have numbers 1, 2, 3, and so on, but you have two, I think they're green, that don't have a number at all. And the numbers alternate, red, black, red, black, red, black. And I believe there are 36 numbers. So you have 18 reds, you have 18 blacks, and then you have 2 greens. So if you simply bet on red or black, your probability of winning is 18 out of not 36, but 38, which is 9/19, or about 0.47. That's the closest to 0.5 that any game of chance will be. But if you play roulette over a long period of time, what can you expect? That you're going to win about 47% of the time. Now, I've seen this proof, I've actually done it when I was in school. If you were a gambler, and let's say you knew the probability of success and failure, and you already know the probability of success is not great in general, right? And your negative expected value. If you wanted to maximize your winnings or minimize your losses, now by the way, people say, well, then just don't play. No, you're going to play. You decide, I'm going to go play today. Mathematically, how do you maximize your winnings or minimize your losses? Anybody know? It's actually a simple proof.
Wait. Can you rephrase it again? Because I'm not sure.
You're going to play. You're not going to sit and watch. You're actually going to sit down at the table, or you're going to put money into the slot.
You have to bet $500 no matter what.
You're gonna bet no matter what. How do you maximize your winnings and or minimize your losses?
Keep making the same bet.
No, believe it, it's simpler. You play one time. If you won, walk away because the expected return is negative. If you lost, walk away because you've minimized your losses, because over the long haul, we just talked about the law of large numbers. Mostly you're playing binomial games. The roulette wheel doesn't remember what it landed on last time. The slot machine doesn't remember what it did last time. So in other words, the probability of winning stays the same. And if the probability of winning is low and the payoff doesn't justify it, you see, if the probability of winning was really low but the payoff was really high, could you gain an advantage by playing enough times? Sure. And we're going to look at that in a moment mathematically. But if you wanted to maximize your winnings, walk away. Now I'm going to tell you a funny story. A few years ago, I won't mention names, but my wife and I and another professor went to a conference in the Nevada side of Lake Tahoe. That's the side where you can gamble, but you can also smoke. That's it. So everything's got a layer of smoke that starts about here. And it was a math conference, and it was called, actually, recreational math. And I went to several seminars, and they were basically about gambling and things I'd never seen. And I discovered the Kelly system, which is actually one of the oldest, wisest system of if you're actually a bettor. And I actually did some research and wrote a paper. It was really cool stuff. But in the evening, my wife had gone to bed, and so me and the other person were sitting, and instead of casinos, everything is computerized. So you can do a slot machine, but it's a computer. So you're doing everything with a computer screen, which is kind of weird. So you put your credit card in to play, which is really dangerous. And so we're talking, and they played, and it was just basically a slot machine. And all of a sudden came ding, 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 and they won a couple $1,000. And we've already been there for 5 minutes. And they were going to, they wanted to play all night. And I said, call your husband. Why? Call your husband right now. Why? Call your husband and tell him you just won $2,000. And they were not happy with me, but they did. They called their husband. They said, why did you do that? I said, now you can't spend it all and waste it because your husband expected you're going to come home. They played for 5 more minutes, I think they lost $1,200. Then they walked away. I said, if I hadn't made you do that, they would have wasted all 2,000 in a few minutes. I've seen this happen multiple times. I've never done it. I would be smart enough to walk away. Why? They just won. I literally on the first try they won. Well, if they played the rest of their life, they're not going to come out ahead. They're only going to come out high mathematically. Yes, there will always be somebody who wins, but the number of losses has to far exceed that, so that way the casino makes money. It's not complicated mathematics. You may never win, but somebody will win. If you play enough, will you win? Probably. Yeah. Will you win more than once? Probably. But will you come out ahead in the long run? No, not in the long run. Because mathematically, the expected value is something that can be calculated. That would be a long-term average. So now let's do something that a lot of you are familiar with, which is a perfect example of this, and that would be a raffle. Now, generally speaking, some organization is holding a raffle. What is the point of the raffle? For you to get rich? No, for them to make some money. The point of a raffle is for the organization to make money. And think of it as something legit. A charitable organization is holding a raffle. They give away all sorts of cool stuff. Maybe it's financial, maybe it's money prizes. But they're supposed to make money on this. That's the whole point of the raffle. So they can, generate funds for whatever there is. Now, you can choose not to play. Agreed? So, let's imagine the following. Let's say that this particular raffle, there are 1,000 tickets sold for, we'll keep it really simple, let's say $500 each. Okay? I love using raffles because they're really simple to understand. The mathematics is usually pretty simple. And here's how it goes. There is one first prize. There are 2 second prizes. There are 3 third prizes. There are 10 consolation prizes. Okay? There's one first prize of $200,000. Wow. There are 2 second prizes of $50,000. There are 3 third prizes of let's say $10,000, and there's 10 consolation prizes of $1,000. Now, the rule of thumb on a lot of these situations is should you play, should you not play? Well, actually, the rule is always this: can you afford to lose that? Anytime you're going to invest money into something that's not guaranteed, in other words, if you go to your bank and you're putting it into a federally insured account, yes, it's absolutely guaranteed. Are you going to make the highest interest in that investment? No, probably the lowest, because it's the safest. So there's something that's not entirely safe. You're going to do some cryptocurrency or something like that. Potentially you could make a lot of money, but potentially you could also lose a lot. Okay? The rule of thumb is always you never do that unless you can actually afford the hit you're going to take by losing it. You don't want to lose it. But it would be really silly to invest next month's rent money or next month's mortgage payment or all of next month's credit card payments on something. I'm going to take a chance. Because if I lose it, now I'm in trouble. Okay? So, there's 2 questions. First of all, what is the expected return for anybody who plays this or buys a raffle ticket? And is it a fair game? This is the definition. A fair game would be that the expectation is the average person will walk away 0. But wait a minute, nobody's walking away 0. Some people are making a lot of money. Most people are losing $500. Kind of have to take that into account. So let's let X equal the possible outcomes of somebody who buys a raffle ticket. You had to buy the raffle ticket. Okay? So are you walking away $200,000 ahead if you win? No, $200,000 minus the 500. Oh. So 199,500. What else? 49,500. What else? 9,500. What else? 500 and what? Mostly negative 500. Ooh. If I don't do that, I'm going to walk away going, wow, people are making money hand over fist. Well, most people walked away. In fact, 984 people walked away $500 poor, right? Most people lost money on this venture. So, what is the probability of each of these outcomes? That's easy. 1 1,000, 2 1,000s, 3 1,000s. What's this one? 10 1,000s, and what's the last one? 984 1,000s, because those probabilities must add to 1. There is no overlap. So, since expected value is defined to be the sum of every possible outcome multiplied by the probability of that outcome, then if X represents the amount of money you win or lose, so another way of thinking about it is the average outcome of everybody who buys a raffle ticket. That's the simplest English. The expected value of X in this case would be 199,500 times 1,000 plus 49,500 times 2,000 plus 9,500 times 3,000 plus 500 times 10,000, and then finally plus negative 500 times 984,000. So let's calculate that, shall we? This is a dollar amount, by the way. Calculator keeps freezing on me. What I do, I'm lazier than most of you. Every denominator is 1,000. So just multiply by the numerators and take your result and then divide that by 1,000. That's less button pushing. Does everybody understand what I just said? This is why you don't want to reduce any of these quotients. So you do times 1, times 2, times 3, times 10, times 984, all divided by 1,000. Does anybody have a number?
Negative 160.
Negative 160. Anybody else have that answer?
Yeah, that's about good.
So you've got negative $160. So that's a dollar amount. Did anybody here lose $160? Was that a possible outcome? No, but it's the average outcome of every single person who bought a raffle ticket. Now, if you're buying the raffle ticket, it's because you're two things. One, you're saying, I want to support that organization. I remember buying a raffle ticket a few years ago. They had like a vintage classic VW Bug that they were just throwing in the raffle, but the raffle tickets were like $50. It was my kid's school, but I think somebody donated this. It was like $50 to win a car that I can now turn around and sell for a lot of money. Sure, I'll pay $50. Now, I knew I wasn't going to win, and I didn't mind spending the $50 because I knew it was going to a good cause. But the thing was, is if you could afford the $160 loss, might you consider this raffle? Yeah, you have a 1 in 1,000 chance of winning 200,000. Well, why not just play the lottery? It's more like 1 in 50 million. your probability of winning the lottery, if you played every moment of your life for the rest of your life, the probability is still that you're not going to win. No. Those numbers are absurd, right? Those are obscenely small probabilities. This is not so bad. Now, I want to make this a fair game. I want this raffle to be such that, or in fact, you could make it this way. It's the philanthropist raffle. I want a positive expected value. Well, everybody can't win, but if I up the prize money, would that change the expected value? Okay, so could I change one number on this? There's 1,000 tickets selling for $500 each. That's not changing. How much money is that? That's $500,000. Could I change one outcome so that the payout is essentially $500,000? Is it possible to do that? Yeah, what would be the easiest way to do this without having to redo the whole raffle? Probably just up the first prize. If the average loss is $160 for 1,000 people, isn't that $160,000? So what if I upped this by $160,000? Would that make this a fair game? Yes. Are raffles fair games in general? No, it defeats the whole purpose of the raffle. So you'll understand that going in. So one of the questions I've asked you on this particular quiz is I've given you a simple game. Maybe we're flipping a coin or we're rolling a die or something simple like that, where if you roll this, you win this much money, but if you roll this, you win this much money, and so on, but you had to buy in. That's one thing we often forget in games of chance. You had to buy in. Oh, I had to pay in order to play this game of chance, and now my winnings need to at least match what I paid in. If they exceed what I paid in, then I came away ahead. If they don't exceed what I paid in, then I came away behind. I've seen this before many times. I'll say, oh, you went and played. I'll say, how much did you win? And you say, oh, I won this much. They'll say, and how much did you lose? And usually it's significantly more. I know for some reason people, I won $1,000, but I lost $10,000. No, you lost $9,000. You didn't win if your losses exceed your winnings, but people remember how much they won. But it's usually they lost more because the probability is such that the longer you play. I teach the mathematics of gambling in many different courses, and I'll go into great detail. I'm not a gambler because I know the expected value is not good. I have bet in my life. I have bet. I used to go to Vegas a lot to compete in martial arts. And it's one of the biggest tournaments in the world. It was held in Vegas every year. And I used to go every 2 or 3 years, all through the 80s and 90s and even into the early 2000s. And I had a friend who bet on football. And the tournament was usually in January, so it was NFL playoffs. So one particular year, he talked me into putting some money on the NFL playoff games. And so it's called a parlay. That's where you bet on a whole bunch of things at once. And you don't have to win everything, but if you win everything, you win big. And so the games are such that I bet 4 different games and I bet on the point spreads. And the first 3 I lost. But if I win the last one, I think I break even. And I still remember it was the Washington Redskins playing the Detroit Lions. And if the game ends in the next couple of minutes, I'm going to break even. And Washington scores a meaningless touchdown in like the last minute of the game. They're already way ahead. And they blew the point spread, so I lost all 4. That was the one. I also bet another time a friend was going to Vegas for the Super Bowl like 5 or 6 years ago. And I said, I'd put $100. This will be an easy one. Put $100, and I lost that one. So I bet on football twice in my life, and I lost both. I don't bet on sports just because you have no control. I'm not a gambler because I know the value. Although I don't discourage people from gambling, what I tell people is know the mathematics of gambling. Because if you don't know the mathematics, you might make silly bets. Anybody ever play blackjack here? Ever, at any point? All right, so you got dealt a 19. I think I'm gonna hit. Probably a bad idea because most everything that occurs will put you over and you've now lost automatically, but 19 is a really good number. 21's the best, but to reach 21, I need a 2. Not a very high probability I'm gonna be dealt a 2. That makes sense? So there are certain bets that are just not really smart. So if you're a gambler, at least be smart on the betting. So main thing about this expected value, again, you have to know, either because you figured it out or you were told, you have to know every value the random variable can take on. The random variable is simply the set of all outcomes. That should be clearly defined in any problem. Also, the probability of every outcome you have to know. And again, that should not be something that's difficult to figure out. Then the expected value is that product added up. In a money situation, we only do this with money. We call it a fair game if the expected value is 0. When we were doing the expected number of tails, There's no money involved. That's not a fair game or not. I'm just calculating the expected value. This is a money situation, so fair game has to do with money. So if you were a gambler and you had the possibility of playing a fair game, you'd say there's no risk. And if I'm a smart gambler, maybe I can come out ahead. Maybe. Now, I'll use cards again, because a lot of people are familiar with blackjack. It's a pretty simple game, right? You dealt 2 cards, you want it to add up to 21. If it doesn't add up to 21, an ace can be a 1 or 11. If it doesn't add up to 21, you can ask for more cards. But you're playing against the dealer, and you don't know what the dealer has entirely. What do you know? You know one of the dealer's cards. They turn one of them up. So the dealer has a 6 showing and you were dealt 18. You're very high probability you're going to beat them. The dealer has a 10 showing and you were dealt a 16. There's a very high probability they're going to beat you if you do nothing. So you're probably going to take a card knowing it could put you over, but it could put you closer to 21. There's risk involved, but you're doing it based on the probability of the other person, but you don't know everything. So that's what I'm saying. There are intelligent and there are unintelligent bets. Now, it seems in the long run, I'm playing against Zachary. It's you against me. And we're both being relatively intelligent. We're not making silly moves. We're not taking a card when we have 20. So we've been playing all day long. At the end of the day, is it fair to say that we should both be breaking even? We're playing against each other. So wouldn't that be a fair game in a casino then? Not exactly. Why? Does anybody know? I ended up with 20. You're the dealer. You ended up with 20. We tied. No, we didn't. You won. Dealer wins all the ties. That's why it's not a fair game. So if I play with perfect precision, I'm not a card counter. I just make perfect choices. I make every choice based on what I see that I have, what I see that you have, the probability that you can do this, the probability. I make intelligent bets. Every bet I made was exactly the right thing, or every I shouldn't say that, every play I made. Should I take a card, should I not? Everything I did was the smartest move I could make. I'm still not going to win the majority of the time because I'm going to lose all the ties. That's why, again, it's not a positive expected value. But if I play smart, I can win a lot of the time. Now, what if I play dumb? I'm going to lose most of the time and, I'll walk away. I have played blackjack in a casino. I mentioned this before. I had fun. On those times I went to Vegas, I had a couple hours to kill. They used to have what are called $2 tables, where you only have to buy in $2. And I would play for a couple hours on $20. And I either walked away with no money, I lost $20, or walked away with maybe $40, $50, $60. Didn't win very much because it's a $2 table. But I played just for the enjoyment and the fun and the thrill of making the bets, knowing, if I spent $20 to go out and do something, to me it was an entertainment expense. I didn't look at it as gambling in that case. And I was, upping my understanding of probability when I'm teaching people. So it's kind of fun. All right, we have one section left tomorrow. Neither harder nor easier, just different. It completes the picture of everything we need to know for this. Hopefully then, at the end of this chapter, some of you guys will be excited about this type of mathematics. It's called combinatorics. If you're a computer scientist, you will probably be taking an upper division combinatorics class, where this would be a small piece of the class. There's way more than what we're doing. This is foundational. But you would do a lot of this stuff to set the stage, and then you'd go off and attack way, way bigger problems. And there are proofs, but they're combinatorial proofs. The proof that I did earlier, right, that's a proof. But we all understood the proof because it's one of these that if this is true, then this is true. It kind of rolls. Some of those steps were not entirely obvious, but it's kind of cool that we could actually do that. So anybody who's had stats before, you should appreciate the whole NP thing. When I teach stats, you know what I do? I do the problem with the coin flip and we calculate the 1.5. And I might even do 4. And we calculate and we get exactly 2. And then I will tell them, in general, this is what it is. And I have to do it that way. I demonstrate it and then I have to tell them. Why? Because in a college stats class, there's no math prerequisite. Would they understand this proof? You guys have gone through calculus and you would not have understood this proof a week ago, would you? I mean, that's not trivial stuff, but the fact that you can understand it now, hopefully this sets the stage for your, your future math courses. You say, yeah, I think I'd like to do some of this. All right, we go ahead and click that off. I will be posting the practice test, hopefully if I can get it right tomorrow.